Hello class, this is CSE-4600, Section 1, Week 12, Spring 2025. Alright, so let's finish off our discussion on files in file systems by looking at how a file system is implemented. So I'll begin the slides right here, and here we go. Okay, so at the user's viewpoint, users are concerned more with how files are named, what we can do with files, what does the directory tree look like, and so on. But what does it look like to the operating system? So here's what it looks like. So we typically store our files on hard disk drives. Solid state drives are now a viable option as well. Oftentimes, sometimes it's just a solid state drive. In other cases, it can be a combination of both. We're gonna be mainly looking at files stored on a hard disk drive, but it can also apply to an SSD. Most disks are divided into one or more partitions. Each partition can have its own independent file system, and there are many different types of file systems. You probably have heard of two of them. One is called FAT. That's called a file allocation table, and we'll get to that in a little bit. The other one is called NTFS, which is what Windows uses these days. Yeah, FAT is an older file system for Windows systems, and as you'll see in a little bit, you're gonna see why Windows no longer really uses FAT anymore, even though for backwards compatibility purposes, it's still supported on every Windows machine. Every Windows operating system still supports FAT, even though the modern day file system being used is NTFS. So what is on the disk? Well, there are multiple. It could be one, or there could be multiple disk partitions, but the very first thing on a disk is called the master boot record. That is used to boot the computer. When you start up the computer, the very first thing that starts up is the basic input-output system, or BIOS. In newer systems, it may be called the UEFI, but it more or less does the same thing. The BIOS has information on it that directs it to which drive contains the operating system. So once the BIOS starts up, it finds and executes the MBR on that disk that contains the operating system. The MBR program finds the operating system that's stored in the next block. That's called the boot block. On that block, there is another program that loads the operating system into memory and starts it up. So in short, when you start your computer, it starts a program that starts another program, and that program starts the operating system. Because the operating system is a big program. And in this bootstrap process, we need smaller programs to help out. We need a program that loads. We need several helper programs just to get the entire operating system loaded. So again, it starts with the BIOS, because the BIOS knows which disk has the operating system. On that disk is an MBR, which then is used to find the boot block that contains the operating system. On that boot block is a bootstrap program that takes the operating system stored on the disk, puts it into memory, and starts up the operating system. Every partition has a boot block, even if it doesn't contain the operating system. The end of the MBR, there is a partition table that gives the starting and ending addresses of each partition. So again, every partition on the disk is used for a file system. And the layout of a partition varies on what kind of file system. The layout of a disk partition varies based on what file system is on that partition, but it's often going to contain the following. The first is a superblock that contains key parameters about the file system. When that file system is read into memory, when that file system is first read, the superblock is going to be read into memory. There's also information about the free space on that partition. And then there is what is called inodes. That is an array of data structures, one per file, telling all about that file. So we have information about the files themselves. Then we have the root directory that contains the top of the file system. And then after all of that are the actual files and directories themselves. So yeah. So among the information stored on a disk is information about that information. The most important issue with implementing file storage is keeping track of which blocks go with which file. And there are various methods for different operating systems. Oh, that's a duplicate slide. And the simplest scheme to store files is called contiguous allocation. So each file is given a sequence of consecutive blocks because the disk does not operate on the level of bytes. Rather, it operates on the level of blocks. How large is a block? It could be any size, but let's assume it's 1024 bytes. So that means if you have a file that's 3.5 kilobytes, it's gonna need 4 blocks. Because again, the disk only operates on the level of blocks. When it reads stuff from a file or writes stuff to a file, it does so in units of blocks. And all those blocks are contiguous, meaning we can only store a file in one place, we cannot store it in one place and then continue it somewhere else. Kind of like how in early memory schemes, we would hold processes in contiguous blocks. And you can probably see what's going to happen next. Like with processes come and go, and they fragment the available memory space into pieces to the point where you have too many small pieces, none of which is whole enough to hold another process. That is called fragmentation, and we have the same exact problem here. But there's actually two kinds of fragmentation. The first one is inside those little blocks. Because the disk operates on blocks, if we have a 3.5 kilobyte file, we're gonna fill the first block, second block, and third block entirely, but the last block is gonna be halfway filled. And that halfway full block, that could be space used for another file, but no. When you store a file, it must start at the beginning of a block. So that half kilobyte at the end of that last file, when we store a 3.5 kilobyte file in a space of 4 blocks, that last block, which has half a kilobyte of unused space, becomes wasted space. We can't use it. This is called internal fragmentation. But we also have external fragmentation. Check this out. When files come and go, they get space allocated in units of blocks on the disk. Time later, those files get deleted, and they leave behind sequences of free blocks. This is external fragmentation, and it becomes a problem if you want to store large files, because if those fragments, or rather, if I may borrow a term from our discussion on memory, these are analogous to holes in memory. So, when those holes are too small, you can't fit large files anymore. So you need some method of defragmentation, or rather compaction, to get all these holes back together into one big hole. And that's actually one of the disadvantages of contiguous allocation. We get external fragmentation, which can be resolved using compaction, but the time it takes to do compaction, it's a long and time-consuming process. At least the advantage to contiguous allocation is that it's easy to implement and easy to find a file. To describe a file requires only two things. At what block does the file begin at, and how many blocks does the file extend for? So file A, let's call this block 0. So this is block 0. File A starts at block 0 and it's 4 blocks long. That means file B, which is 0, 1, 2, 3, 4. That starts at block 4 and it's only 3 blocks in size. File C, that is block 7 and it's 6 blocks long. We only need 2 values to describe every file on the disk. At what block does the file begin, and how many blocks does the file occupy? You also only need one seek operation to find a file, because once you're at a block for that file, you're at that file already. You don't have to go searching for other blocks across the disk, because all the blocks for that file, they are all in one place. There is another issue, and it parallels one of the issues with contiguous memory allocation. What if your file grows over time? If you allocate space for a file, when you allocate space for a file, let's go back to processes. When you allocate space for a process, you're gonna find some hole in which to fit that process based on whatever allocation algorithm you use. Do you find the largest hole available, or do you find the smallest hole that's just able to fit the process? Because if a process needs more memory as it runs, if you put it in a large hole, you basically gave that process more space to expand into if it needs that space. And the same is true with contiguous allocation for files. If your file must grow over time, the best thing you can do is put it in a hole in which it can expand. A more better option would be to account for that growth and allocate that much space. So if we know that a file is going to grow to like 20 blocks in size, but it's only like 3 blocks in size right now, let's just go ahead and allocate 20 blocks of space for that file. You can imagine the same exact issues from memory allocation affecting files here. If we run out of space for that file to grow, then we can't save the file properly anymore. But if the file doesn't grow, then that's just more wasted space. There are situations where these file size concerns are a non-issue, and they mainly stem from media that is read-only. CD-ROMs are read-only media. That's not what ROM stands for. It stands for read-only memory. But the point is, it's read-only. We can't write to it. We can't change the size of a file. So once that file is written, it's never going to change size, so the concerns regarding file size of files shrinking and growing, they're never going to apply for read-only memory. They're never going to apply for like CD-ROMs. Linked list allocation is another way to store files on a disk. So once again, files are stored in blocks, and with contiguous allocation, all those files are stored in blocks that are next to one another. So if a file needs to grow, but there's no space for that file to grow, we have a problem. Linked list allocation actually eliminates that issue of file growth. But it also eliminates another issue where we have these holes in the disk, where we have holes of free space that can be subject to external fragmentation. With linked list allocation, the first block of the file contains a pointer to the next block for that file. And then that block has a pointer to the next file, and so on and so forth until we reach the final block whose pointer is null. So now we have a file whose blocks can be anywhere in memory, or rather anywhere on the disk. Kind of like how processes that use paging can have their pages anywhere in memory. Under this scheme, external fragmentation is impossible because your disk is fragmented. No problem. We'll just use what's there. We'll just use whatever space is available. No problem, because we have pointers that can go from one block to another. Doesn't matter how far apart those blocks are. Because a file's blocks can be spread across the disk, every block on the disk can be used. However, we are still subject to internal fragmentation. That last block is always gonna have some wasted space, unless you're able to fill it like absolutely to the brim. There is another disadvantage that I'll get to in a little bit, but with contiguous allocation, you needed two values to describe a file. Where does a file begin, and how long is that file? With a linked list, you only need one value, and that is the starting block of the file. Because to get to all the other blocks of that file, you just have to follow that chain of pointers to get to the next block after that, and the next block after that, and the next block after that. This makes it great for sequential access, where you have to follow a file one block at a time. But the problem with linked list allocation is that random access is harder to do. You want to find the 12th block of a file? Well, you have to go through the first 11 blocks of the file first, one block at a time, until you get to that 12th block. To find the kth block in general requires going through the first k-1 blocks before that. So, random access is harder to do with linked list allocation. Because the file is stored in units of blocks, let's say it's 1024 bytes, some of that space, just a little bit, is needed for the pointer to the next block. This means every block stores slightly less than the full size of the block, because some of that space is used for the pointer. If, for example, we are using 4 bytes to store the pointer, that means each block is only able to store 1020 bytes. This is assuming we're using 1024 byte blocks, and the pointer is 4 bytes large. It means when it comes to transferring blocks to and from the disk can only transfer in blocks of 1024 bytes. So when we read one block, there's going to be 1020 bytes that we can read, but we're missing 4 more bytes. So we have to go to the next block after that to get the first 4 bytes of the next block. This is just a few extra steps of reading, copying, and writing that we have to do because, again, some of the space for each block is taken up by a pointer. It's not a lot, but it does make copying data more difficult. It just adds extra steps. Here's the next thing we can do. Linked list allocation using a table in memory. So here are the problems so far. Contiguous allocation has a problem with disk fragmentation. linked list allocation has an issue with random access. And by extension, with linked list allocation, we are taking a little bit of space from each block to use for a pointer to the next block. What if we just took all of those pointers and put them in another table, so that way every block is able to use the full block of space available, no wasted space for the pointer. So we have a table of pointers to every block for that file. Where do we store this table? Let's just say we store this table in memory first. So this is an improvement on linked list allocation. So instead of each block containing a pointer to the next block, we have a table of pointers in memory. So we had these two files previously. File A was stored in blocks, physical blocks 4, 7, 2, 10, and 12. File B was stored on physical blocks 6, 3, 11, and 14. We can put those tables, we can put in a table those pointers, and now we have what is called a file allocation table. So what does this table say? Well, we know that file A starts at block 4, and what's the 7 mean? That 7 is the next block for file A. So if we go to entry number 7, it gives us the block at which the file continues. So the file A starts at block 4, and the next block is block number 7. The next block after block 7 is block 2. The next block after block 2 is block 10. The next block after that is block 12. And the next block after that is -1. Oh yeah, that -1 is used to denote the end of a file. So, these arrows, if we start at block 4, that is the starting block for file A. If we start at block 6, that's the starting block for file B. And once again, -1 is used to signify the end of a file. This, as I mentioned, is called a file allocation table, and this table is stored in memory. The advantage of a file allocation table is it's easier to do random access, because instead of jumping from block to block, we just have to go from table entry to table entry. So it's easier to do random access, even though we're jumping from row to row in the table. At least we're not jumping from block to block, which is a lot slower. Like with linked list allocation, specifying a file requires only one number, the block at which the file starts. There is a disadvantage to the file allocation table, and it is this. This table needs to be loaded into memory. Oh, and by the way, that table is not for the file being read. So this table represents not only the blocks used by files, but it represents every block on the disk. You see the problem now? Back when storage space was at a premium, where, say, a 40 gigabyte drive would have been a luxury, and even before that, it was expected that you would store your files on a floppy disk, and the hard disk drive would have been a luxury. At some point, hard disk drives just became larger and larger and more capacious, and then we got 40 gigabyte hard drives that felt like a luxury. The reason why I say 40 gigabytes is because that's actually the size of the drive on our family's first ever personal computer. And I'm pulling that out as just a random stat, just for reference. So, we need space to store the entire table. And again, the whole table stores information for every block on the disk. The larger the disk becomes, the more entries you need in the table, the larger the table you need. If we assume 1 kilobyte block size and 3 bytes minimum per entry, the store, a file allocation table for 1 megabyte requires 3 kilobytes of memory. Not a lot, but it starts to become ridiculous the larger the disk becomes. For a 1 gigabyte, to store the file allocation for 1 gigabyte of disk space requires 3 megabytes of memory. To store 1 terabyte's worth, to store the file allocation table for 1 terabyte's worth of disk space requires 3 gigabytes of memory. Which means in theory, if you have a 1 terabyte disk on an old system that used the file allocation table for its file system, you would run out of memory instantly. Not very practical. And although all versions of Windows support FAT, it doesn't scale well for a larger disk size, which is why Windows has since moved on to the NTFS file system. Yeah, we don't use FAT anymore because just too much memory needed to store the entire table. So what if we don't do that? So with the file allocation table, you store in memory a table that describes what blocks are being used by what files. What if you could write a table, have it be part of the file, but that table that is part of the file describes it has pointers to all the blocks used by that file. But we only need pointers to the blocks that the file actually uses. This is called indexed allocation, and an example of this would be the Unix inode. So we have a data structure called an index node or an inode. This data structure contains the file's metadata or attributes, but it also contains addresses to each. It contains the addresses for each block that the file uses. So we have an address to disk block 0 that makes up that file, and disk block 1, 2, 3, 4, 5, and so on. We only need to store the addresses for the file's block, so we don't need to store anything for any other file. The inode here, we only need to load the inode for a file into memory if we need to open the file. So instead of having a table for every block on the disk, we only need to load a table as needed. So we're limited to how many files we can have opened at a time. The disadvantage of an inode is this. An inode only has space for a fixed number of disk addresses, which can put a limit on how large a file can get. But here's the trick. What if we could nest these tables? So this inode is merely a table of pointers pointing to all the blocks that make up a file. What if we could take one of those pointers and have it point to another table of pointers? And then those pointers point to more blocks on the disk. Now we can support larger file sizes. Turns out NTFS follows a similar scheme to this, where we have this table of addresses, but some of those addresses point to more tables. So we have nested tables now. And the Unix inode would look something like... It turns out the Unix inode looks something like this, where you have 15 pointers in the inode. The first 12 pointers point to data blocks. The next 3 pointers after that point to indirect blocks. So the 13th pointer points to a table of pointers. The 14th pointer points to a table of pointers, but those pointers point to their own tables. of pointers. And then those pointers point to data blocks. The 15th does this at 3 levels. And because this is exponential, we can get files whose sizes are on the order of gigabytes. Now we can support very large files. And all it takes to keep this loaded is however much space is needed to load the inode in the first place. You might have to load extra space for the nested tables though. But yeah, the beauty of the inode is that we only need to load this into memory if we need to read the file. Let's talk about directories real quick. Before a file can be read, we of course gotta open it. When a file is opened, the OS uses the path name supplied by the user to locate the directory entry on the disk. The information from the directory is used to find the disk blocks. And depending on the system, the information for a file may be the disk address for contiguous file allocation, the number of the first block for linked list schemes, or the number of the inode for inodes. In all cases, the main function of the directory system is to map a file name onto the information needed to find the file. And a related issue to that is how to store file attributes. Every file system maintains various file attributes or metadata, and it must be stored somewhere. And one option is to store it as part of the directory entry. So, a directory is simply a listing of every file and that file's metadata. So each entry contains, well, among other things, the file name, the metadata for that file, and at least one disk address that points to the file's blocks. For systems that use inodes, another option is to store the attributes as part of the inode. So, the inode, again, is just a data structure that contains the file's metadata and the pointers to that file's blocks. So far, we have assumed that file names are short, and with older files and with older operating systems, this was the case. MS-DOS supported file names that were up to 8 characters large, with a file extension that's at up to 3 characters. In Unix version 7, file names were up to 14 characters long, and that already included the file extension. Most systems now support longer file names. How? Well, one solution is to have a large maximum file name length, like 255 characters. So, for each directory entry in the file system, we reserve that many bytes of space for each file's directory entry. However, this is wasteful because not every file needs that long of a file name. So an alternative to that is to just give up on the idea that all directory entries on the file system should all be the same size. So, each directory entry for a file system consists of 2 entries that are all a fixed size. The length of the entry, the file attributes that are in a fixed format, and the file name. The file name can be as large as it needs to be. Here's the thing though. One word in the entry for a file can store multiple characters, so there may be some wasted space here. That's what these gray boxes are for. Also, we need an extra character to denote the end of a file name. That is a null character. That's what the little X's in boxes are for. So, for each file name, we need to store an additional character that denotes we've reached the end of the file name. The issue here is this. If we remove a file, that results in a gap in the directory, and the problem is that may not always be the right size to store another file in there, because all of these directory entries are all different sizes, we now have the same issue of external fragmentation once again. We had external fragmentation on the level of processes in memory. We had external fragmentation on the level of files stored on a disk. Now we have external fragmentation on the level of directory entries for a file system. What the heck? There is an alternative to that, and that's just to keep the size of each file's directory entry the same size. Instead of storing the file name in the directory entry, we have a pointer to the file's name stored on what's called the heap. This also resolves another issue where if we have directory entries that are as large as they need to be, it's possible that a directory entry for a file could span 2 pages, so you can have a page fault just trying to access a file. So the alternative is to keep the size for each file. So again, the alternative to having directory entries be as large as they need to be is to keep directory entries all at a fixed size. Don't store the name in there. Store a pointer to where the name is actually stored, and that location is the heap. And now you've passed on space management passed on the issues of space management to the heap. For example, if you delete a file, you now gotta delete the name for that file from the heap. Page faults can still happen when you're processing file names, but unlike when storing file names in the directory entry, there is no wasted space. So you see all these gray areas here? In a sense, that is more internal fragmentation at the word level just to store file names. We don't get that issue if we store file names on the heap. We're almost done here. So, a file system has directory entries for every file stored on it. If we want to find a file with a specific file name, one easy way, which will turn out to be slow, is to compare entire strings and see if they match for each entry in the directory. That is basically linear search, which is okay for small directories, but when we get to file systems that store like millions of files, linear search starts to become an issue. So there's one way to speed up searching for large directories, and that speed up can be achieved by using what's called a hash table. So think about it like this. Let's suppose we have a table that can store 64 entries. In practice, this would be something larger, but let's say it's 64 entries. That means we have entries to store up to 64 unique files, which doesn't sound like a lot, but just let's just roll with this example. Instead of searching for a file by its file name, we search for it by using its hash. What's a hash? So, a file name is nothing more than a sequence of values that encode the characters that spell out a file name. So, every character in a file name has a ASCII value associated with it. One way to get, I guess a simple way to get the hash value is to take all those numeric representations, add them all up, divide it by 64, and then get the remainder. So again, every ASCII character has a value. Just add up all the values, divide the sum by 64, and get the remainder. And that is one way you could get a hash value. There's probably other ways to get the hash value, but let's just roll with that example for now. Now, you have converted a file name into a number that ranges from 0 to 63. You use this hash value to search the table for that file's entry. let's say we have a file whose hash value is 31. So you search for the 31st entry in the table, which is technically the 32nd because we start counting at 0. What's the 31st entry? We search the hash value in the table. If we find an entry for that hash value, then that means there is an entry for that file name. That means we found the file on the disk. There is one possible issue with this. What if we have more than 64 files? That means by the pigeonhole principle, we have 2 files that have the same hash value. This is called a hash collision. So, if we have 2 files whose hash value are both 31, what do you do with those 2 files' information? Well, instead of storing it in the table, you have a pointer to a data structure that stores those files in a list. So if you have a hash collision, you search for the table, you search in the hash table for the address to that list. And then in the list, you compare each entry one by one to find the correct file. We've basically reintroduced linear search here, but at least it's done on a smaller set of files. The ones whose hashes are the same. My point is, if you are storing millions of files in a file system, chances are you're going to want a hash table because it's going to speed up looking for files. And that concludes our discussion on files and file systems. Now we can begin looking at deadlock. So this is probably going to be our last topic for operating systems. So let's begin the slideshow for that, and there we go. So now we have to look at the operating system as a resource manager. Computer systems are full of resources, and many of those resources can only be used by one process at a time, such as printers, scanners, drives, slots in an internal table. If 2 processes try to use the same resource, you might get incorrect output, or you might get, at worst, data corruption. Additionally, many processes may need multiple resources just to do their job. We are now looking at the operating system as a resource manager. The operating system must then grant a process exclusive access to certain resources. When a process needs a resource, it must ask the OS, "Can I use this resource, please?" And that request may be granted right away, or it may be rejected. Why would the operating system reject a request for a resource? Simple, because some other process may be already using it. Think about it like this. Ever just circle the parking lot trying to find a parking spot? Think of the parking spots as resources. 1 car at a time per parking spot, though there are some ways to cheese that in very rare cases where you could fit like 2 smart cars in one space. But generally speaking, 1 car per parking space, that is an example of resource management. And in some fancy parking garages, there are overhead lights that indicate whether that space is taken or not. At the front of those same parking garages, there may be a sign that says, "This lot has 31 parking spaces left." I guess my problem with those overhead lights, they are red if they are taken and green if they're not taken. What if you're colorblind? That's just the one thing I always think about, all the time. Colorblind accessibility. Yes, I can see colors just fine. I know the difference between red and green, but I always have to assume that the next person can't tell the difference. So, colorblind accessibility is one of the biggest things on my mind especially whenever I design my own PowerPoint material. It's also why I'm scared to color code things sometimes. My point is this. we have processes asking for resources, the operating system must either grant that request or reject it. The problem is, the operating system must not hand out resources willy-nilly, because you could have one process that's using a resource that another process needs. That process might have another resource that the first process also needs. That is a situation called deadlock. You may have noticed this picture of like cars stuck at an intersection. These cars are trying to look here. See these cars? They're trying to move forward, but they're blocked by these cars. They're trying to move forward, but they're blocked by these cars that are actually out of frame. These cars are trying to move forward, but they're also blocked by these cars. And these cars are trying to move forward, but they're blocked by these cars. It's a loop! So that's actually one of the properties of a deadlock. There is a circular loop of I need this, but I need this, but I need this, and someone else is already using it. That is one of the conditions for deadlock. We're going to look at the others in a little bit. Deadlocks can occur with both hardware resources, such as access to a printer, or software resources, such as access to a record in a database. In either case, studying how deadlocks can happen and how to prevent them, it's an important topic in not just operating systems, but in other fields of computer science. And even more so in real life, where if you have a poorly programmed traffic light, you can have this happening. So, resources. The things that a process needs access to are called resources. Resources are anything that must be acquired, used, and released over time. Resources can include hardware or a piece of information, such as a record in a database. In some cases, there can be multiple instances of the same resource. Resources come in two types, preemptible and non-preemptible. Preemptible resources can be taken away from a process without ill effect. Non-preemptible resources cannot, without causing bad things to happen. What kind of bad things? Like, bad things such as data loss. We actually seen a few preemptible resources. The CPU is a preemptible resource. If you think of the CPU as a resource, processes take turns to use the CPU. And especially more so if they're doing it round robin. And the one thing that we talked about a process is this. If we need to stop a process at any time, we save the values that are stored in the registers into what's called a process control block. The process stops running and we allow for another process to run. So processes, especially if they're round robining, run on the CPU for a fixed amount of time. When that time is up, it's time for another process to run. That process's register values are saved. The next process's register values are loaded onto the CPU, and now it's that process's turn on the CPU. Mom says it's my turn on the CPU. Memory is also preemptible because the pages that make up a process's memory space, we just move them back and forth from memory to the backing store. If a process goes idle, then that means those page frames that are needed to store that process's memory, they're just being wasted on a process that's gone idle. So, what we can do is preempt those page frames. We take the pages loaded in those frames, put them back on the backing store, and now we have page frames available to be used by other processes. So the CPU and memory are preemptible resources. If we take the CPU or memory away from a process, the process has no problem with that because we're able to save, in the case of the CPU, we're able to save the values stored in the registers. In the case of memory, we can store those pages back on the disk until we need to reload them back into memory again. So those are preemptible resources. For both the memory and CPU, preempting either causes no ill effects. If anything, the process simply needs to wait its turn to use the memory or CPU again. What about non-preemptible resources? There are a few examples, such as a CD drive. If a process is writing to a CD, if we preempt the CD drive, that is, if we take away the CD drive while a process is using it, we're gonna end up with corrupted data on the CD drive. No, on the CD. The CD drive just reads the CD. If we write to a CD and we preempt that drive in the middle of a write operation, we've just screwed up the data on the CD. Similarly, if we were to print out a document on a printer, if we preempt a printer while a process is using it to print stuff out, then we've just screwed up the printout. What counts as preemptible and non-preemptible also depends on context. Memory is preemptible because we can swap an entire process and put it on the disk, or we can swap out pages of a process memory space and put that on the disk. But that assumes that the system is capable of paging or swapping. If a system cannot swap or page, then we cannot preempt memory because there's no other place for those memory contents to go. Can't we store it on the disk? Well, yeah, but that's already swapping. If a system is unable to swap, if a system isn't capable of swapping or paging, then memory becomes a non-preemptible resource. It must be allocated to a process and it cannot be taken away. In general, deadlocks involve non-preemptible resources. If we get a deadlock using preemptible resources, we just resolve it by reallocating resources or suspending processes until they're able to run again. If we have deadlock because processes are trying to fight over memory, then we just suspend some of those processes, let the other processes run. Basically, those processes gotta wait their turn until it's their time to run. So with preemptible resources, we resolve deadlocks by reallocating resources. With non-preemptible resources, we cannot reallocate resources at all. There is a 3-step process for how resources are used. Step 1, request the resource. If the resource is not available, like it's in use, wait for a while and then ask again later. Once you got the resource, you gotta use the resource. And once you're done with the resource, you gotta release the resource. Pretty simple, right? When it comes to a resource being rejected, that process is blocked because it can't do any work. Once that resource is available again, the process is awakened. What can also happen is there is a function that is called for requesting a resource. What could happen at the level of the process is that request returns an error code, and what happens next depends on the calling process. We're just going to assume that when a process requests for a resource and that request is denied, the process goes to sleep. When it comes to the nature of requesting a resource, some systems have a request system that processes must use. Other systems only regard special files that can only be opened by one process at a time as a resource. In those cases, you basically request for a resource by using the open and closed system calls. Well, you request for a resource by using the open system call, and you release a resource by using the closed system call. If a process calls open on a file that's already used by another file, that process is blocked, the process goes to sleep, and it waits for its turn to open the file. For some resources, no system calls are needed. It's up to the processes to manage resources themselves. We can do this using semaphores. So semaphores are values that indicate how many of a resource is available, and there are two operations that are called down and up. We call down when we call down, it decrements the available resources by 1. If that was 0, then the calling process is blocked. Calling up increments the available resource by 1. If another process was blocked, that process is awakened. This also works with any number of resource types. With two processes, things can change depending on the code that is written. Depending on how the code is written, processes can become deadlocked. With the code here, processes acquire resources in an order that actually prevents deadlock. But on the code on the right over here, so the code here, figure A, that code is written to prevent deadlock. But the code on the right, that code actually has an issue that results in deadlock becoming a possibility. And what can happen is this. One process requests a resource that's already used by another process. That process is requesting a resource that's already being used by the other process. This is a loop. In graph theory, this is known as a cycle. And if you have a cycle like this, you have deadlock. Here is the definition of deadlock. A set of processes is deadlocked if each process in the set is waiting for an event that only another process in the set can cause. Because all processes are waiting and assumed to be sleeping, no process can wake up one another. For our deadlock model, we are going to make a few more assumptions. 1. Processes are single-threaded and no interrupts are possible to wake up blocked processes. 2. We're dealing with what is called resource deadlock. Called such because processes are waiting for processes that are holding up other resources. This is the most common type of deadlock, but it's not the only kind. And I talked about that circular loop. I talked about that cycle. When it comes to the conditions for deadlock, that's called a circular wait. This process is waiting for this resource to become available, which is held by this process, which is waiting for this resource to become available, which is held by this process. It's a loop. If we have at least two processes in a cycle like this, that is called a circular wait. They're waiting for each other, but they can't advance. The other conditions are as follows. Mutual exclusion. Resources are available or assigned to exactly one process at a time. Hold and wait. Processes currently holding resources that were granted earlier can request new resources. No preemption. Resources given to a process can only be released by that holding process. And circular wait as shown here. So, the conditions for deadlock are such that A cannot release R1 until B releases R2. So, let's back up. A needs resource 2, but it's held by process B. Process B needs resource R1, but it's held by process A. A cannot release R1 until it gets R2, but B cannot release R2 until it gets R1. I need this. No, give me this resource first. No, you first. No, you first. That's the kind of circular loop that allows for deadlock to happen. Again, there are 4 conditions: mutual exclusion, hold and wait, no preemption, circular wait. Those are the 4 conditions for deadlock. But here's the thing. If we eliminate even just one condition, that is enough to keep deadlock from happening. We're going to look into what condition we can eliminate in a little bit. But let's explain what this diagram is. So we can visualize deadlock using a graph. Processes are circles, resources are squares. If a resource is allocated to a process, then we draw an arrow from the resource to that process. If a process requests a resource, then we draw an arrow from that process to that resource. So R is allocated to A. That means A is holding resource R. B is requesting resource S. And if we have a loop like this, if there is a cycle in the graph that involves at least two processes, that's a deadlock. So here's an example of resources and processes. They're all requesting resources, and it's possible to get a deadlock. So, process A requests resource R. Process B requests resource S, and process C requests resource T. And now we have resources R, S, and T allocated to processes A, B, and C. Process A also needs resource S, but process B also needs resource T. And then process C also needs resource R. And now we have a loop. Look. Right? Now we have a circular loop. In our graph, we got deadlock. There's actually a way to eliminate this deadlock, and that is to deny one of these requests. Here's how. We can fulfill these requests in a different order to prevent deadlock. So remember, the requests are as follows. Process A needs resource R and S. Process B needs resource S and T. Process C needs resource T and R. If we just fulfill those in that order, we get deadlock. If we fulfill them in a different order, then we can prevent deadlock. So remember, process A needs resources R and S. Process B needs resources S and T. Process C requires resource T and R. We know what each process needs. So let's just so instead of doing it in the order of A requests R, B requests S, C requests T, A requests S, B requests T, C requests R, let's do it in a different order. Let's give to process A both resources R and S. At the same time, well, actually, no. Let's do it in this order. Process A requests resource R, and that is successful. Process C requests resource T, and that is successful. Instead of allocating resource S to process B, we give it to process A first. Now, the next step is to have process C request resource R, which is held up by A. Is that a problem? Actually, no. Because faulty arrows. This is a one-way path that starts at T and ends at A. Nothing about this configuration of requests and allocations, nothing about that path loops on itself. So, what's gonna happen is this. Process A is gonna use resources R and S. After some time, process A is gonna release those resources, and now they're gonna become available for the other processes to use. So, let's just say process A first releases resource R, and that's available for process C. So now we reverse this arrow to point to process C. After that, process A no longer needs resource S, and it deallocates it, now it's free to be used by process B. Just by changing the order in which resources are requested by processes, we can prevent deadlock. I'm going to end this with the 4 different strategies for dealing with the deadlock, and we'll look at each one in more detail next week. The first strategy is to ignore the problem. If you ignore the problem, then the problem will ignore you, right? The next strategy is to let deadlock happen, detect whether it happened, and recover from it. The next strategy is one that we just saw a taste of: allocating resources in an order that would that would avoid deadlock entirely. And the last strategy is to look at these 4 conditions for deadlock and see whether any one of them can be negated. Because, again, there are 4 conditions to deadlock, and if we eliminate even just one, we have eliminated deadlock. So, again, the 4 strategies are: ignore the problem, let it happen, and detect that it's happened, and recover. Alright, let me back up. The 4 strategies to deal with the deadlock are as follows. 1. Ignore the problem. 2. Detect and recover. Let deadlock happen, detect whether it has happened, and find some means to recover from it. Number 3. Allocate your resources in a way that avoids deadlock. Number 4. Of the 4 conditions for deadlock, find a way to negate one of them. Because if you eliminate just one condition for deadlock, you have broken the deadlock. We'll look into that once again next week. I am going to assign you your set of questions for file systems, and they are as follows. Question 1. Systems that support sequential files also have a rewind option. It's rewind time. Can you have rewind time on a system that supports random access? Do you need a rewind option if a system supports random access? That's number 1. Number 2. Suppose a system only had one directory, one level of directory. You cannot make subdirectories, but it allowed for arbitrarily long file names. Can you organize files still? Is it still possible to organize files in a hierarchical way? Think about that. Number 3. Some systems provide a separate rename operation to rename files. How is it different from performing these 3 steps? 1. Create a new file with a new name. 2. Copy the contents of the old file to the new file. 3. Delete the old file. 4. Contiguous allocation leads to fragmentation, since the last block of a file isn't always completely full, leading to wasted space. Is this external fragmentation or internal fragmentation? So those are your 4 questions, and they're all pretty simple, but we can talk about these questions next week as well. So we're gonna move on to deadlock, which is gonna be our last big topic of discussion for the class. So that's gonna be it for today, and yeah, these questions will be due next Friday. I'm gonna give you a little bit of time to answer them. Okay, that's gonna be it for this week. We'll continue our discussion on deadlock the following Tuesday, and yeah, your final project is going to be writing a deadlock detection program. So that's probably gonna be for week 15 though. Right? That's it for this week. Take care, and see you next week.